Hello, Gen Chem tribe. We are now getting into solution chemistry. And the reason why we need to talk about solution chemistry is that, it is, hard to react molecules of different phase with one another. Problems with maybe surface area, such as a solid, or containment, as with gases. To ensure excellent reactivity, and basically increase statistical, probability of starting materials running into one another. All the starting materials should be of the same phase. Now, it's still problematic, solids and solids reacting with one another and things of that nature, but what we want is a solution phase. So the common reaction phase is one where all the starting materials are in a solution, dissolved in a solution. So that allows, now these molecules are the same phase, and now they can, react with one another on a one-to-one basis, in this, solvent, which is, inert to the process. So, those are some of the terms, going forward is we have solute. Solute is the molecule that is being dissolved. This is called dissolution, as far as being dissolved. And then you have the solvent, is the molecule that is doing the dissolving process, right? The dissolution process. So those are the two components that we have. And solute can be any phase. We can have solid, liquid, or gas. Solvent as well can technically be any phase. For us, the solvent will always be in that liquid phase. And you put them together and you have what's known as a solution. So we have a mixture of solute and solvent. right? We've already talked about some of these types of mixtures, right? We could have, homogeneous solution, which is, a solution that we cannot tell, visually that it is a mixture. And then we have heterogeneous. And this is a solution that you can tell visually that it is a mixture. We also have within these types of solutions, we have stock solutions. These are solutions that are very concentrated, or in other words, contain a lot of solute. And then you have dilute solutions, which are solutions that have been diluted by the addition of more solvent. So if you take, a stock solution and you add solvent, you now make a dilute solution. So there's a couple terms. We'll talk about some more terms as we go through. But that's kind of the beginning of this idea of solution chemistry. When creating solutions, and in terms of solution chemistry, we want homogeneous solutions where all the solute is dissolved. So in creating solutions, you basically want to match forces of attraction between the solute and the solvent. So we're looking at a like dissolves like scenario. For example, methanol is very soluble in water. And we could ask the question, why? And it's because they both have similar forces. So it's this hydrogen bonding motif, right? That we have our OH, and we have our H2O, and both of these are hydrogen bonding type molecules, and so that's why methanol is very soluble in water. It's that like dissolves like. So H2O is a great solvent for basically, small molecules with hydrogen bonding forces or groups within, the molecule. So groups would be like, an OH, where here this R group here is, the rest of the molecule. So we have this, other part of the molecule, but we're just seeing this group here, this ROH group. Another one that we see is the NH group, the CO2H group as well. And then lastly, looking at carbon-oxygen double bonds within a molecule, as well as carbon-nitrogen double bonds within a molecule can all participate in hydrogen bonding with H2O. So we're looking for, these groups in a molecule, and if we see these, then these would be very soluble in H2O. Just as a side note, this RCO2H, just to draw it out, has this type of structure. So those are the same molecule, just expanding on it. So because of that, these all are extremely water soluble type molecules. As you add carbon atoms to the solute, we start to see less solubility, or less H2O solubility is observed. And this occurs right around carbons being, greater than or equal to 4 within a molecule. Now, if you offset the number of carbon atoms with hydrogen bonding groups, then you will still observe, good solubility. So, for instance, if we have, C6H12O6, right? And this is common, formula for sugar, sucrose, right? And, putting it into water, it readily dissolves. But it has 6 carbon atoms. And with that, that's this offset idea. If you knew what the structure looks like for for sugar, for specifically glucose, right? We would have this type of 6-membered ring. And what we have is then a lot of OHs that are actually around the ring. So if we look, right, we have 1, 2, 3, 4, 5. So we have 5 hydroxides, or well, I shouldn't say hydroxide, we have 5 OHs for 6 carbons. So still very soluble in water. So you can have that idea of offset too, as long as you have as many OHs as you do carbons, or roughly the same, you're going to still see very good water solubility. And that's even getting then into much actually larger molecules, such as peptides and proteins, enzymes. These molecules are very, very large, and they have tons of these polar hydrogen bonding functional groups, such as carbon-oxygen double bonds. We have nitrogens as amines, as amides. We also have, alcohols in there, as well as all these amino acid side groups that come into play. So we could offset that with these hydrogen bonding functional groups. So, if past this idea of, carbon count being, greater than or equal to 4, with, only one, polar group, such as, our OH, CO2H, NH, etc., then we want to pick a molecular solvent. With dipole forces. So if we had if we had here pentanol and looking at dissolving it in water versus dichloromethane, we do have the hydrogen bonding group that we see on the end. And water, as we know, is also hydrogen bonding, so it's a natural selection to just pick H2O. But we have this huge tail here where we have carbons equal to 5. And that's why we are going to see decreased solubility in water as a result. So this molecule is more dipole-dipole, where you would have kind of this, delta plus end and this delta minus end. In terms of that dipole, it's more dipole-dipole-like. So CH2Cl2, dichloromethane, is the best choice. It also has dipole-dipole. So you do have to be wary of the carbon count and the amount of hydrogen bonding groups are on that particular solute. So if the molecule possesses dispersion forces as its lone force, then you need a molecular solvent with dispersion forces. So if we were to look at hexane in water versus dichloromethane versus carbon tetrachloride. Here we have our dispersion forces. And going across the row here, we have our hydrogen bonding. We then have dipole, and then on the end with the carbon tetrachloride, this would actually be dispersion, with all those carbon chlorine bond dipoles canceling one another out. So we would pick carbon tetrachloride. We have a good like dissolves like. So for these molecular solvents, just some examples of them. Ethyl acetate, is a good polar solvent, such as chloroform, dichloromethane. And there are a lot of others out there as well. So these would all be ones with dipole molecular solvents. And then we could look at, for example, actually hexane is actually a good example of a dispersion solvent. Let's get this chart set up right. So that's hexanes. Another common one we use is diethyl ether. Which looks like this molecule. And then lastly, one that we just utilized above is carbon tetrachloride. And so these are dispersion molecular solvents. And there's, like I said, there's a bunch more out there, but here are just a few examples of them. So one last type of solute that we need to talk about is ionic solutes. And ionic solutes are always the most soluble in water. There are ionics, that are not soluble. But when we're thinking about an ionic solute, we really want to pick H2O. That's always where we're going to see in the best solubility. And ionic solutes in H2O generate new forces of attraction. Which is why ionic salts, tend to be so soluble. So if we look at sodium chloride, dissolving into H2O, we get, something that we could write like this, but really there's really more to it, that really these ions are dissociated from one another. So to write, NaCl aqueous is the same thing as saying Na plus 1, that's aqueous, and Cl minus 1, that's aqueous. And that's that idea of that they're really dissociated from one another. So when we look at these ions dissolved and try to come to grips with the fact that sodium chloride has the strongest forces of attraction, electrostatic forces, and those electrostatic forces don't really match with water and its hydrogen bonding forces, what we find is there's a new force of attraction that actually occurs. And so ion dipole forces are produced when an ionic solute dissolves into H2O. So we have these new forces of attraction. These new forces are basically what creates the solution and dissociation of the salt. So if we look at those two ions, the sodium and the chloride, for the sodium, the water molecules are going to be surrounding the ion, encapsulating the ion, right? We know that because the salt disappears by visual eyesight. And if we look at, our, name as far as ion dipole, we know that the water molecule has a dipole, with the oxygen being more delta minus, and then on the other side, the hydrogens being delta plus. So we have those polar setup for the H2O. And it's this delta minus Na plus interaction that is the ion dipole force. And so I'm only showing 3 H2O molecules here, but you got to kind of imagine there's, H2O completely surrounding the sodium, all of them participating in that type of ion dipole force of attraction. And we can do the same thing with the chloride, which is negative. And now we can just, organize our water molecules with their dipoles a little bit differently. With now not the delta minus end, but really the delta plus end that is going to be pointing in to the chloride. And that's now where our ion dipole force comes from. So, there are no ionic liquids out there that we're going to be dealing with. So when trying to figure out what, solvent is the best choice for an ionic molecule, well, your choice is always going to be H2O. And so this brings up kind of the last bit for this introduction, where we have mode of dissolution. Or, how a molecule dissolves, is related to, again, forces of attraction. For most molecules, there is simply an exchange in forces, meaning we have, both solvent and solute participating in forces of attraction with one another. So in that first example of methanol and water, the methanol by itself is hydrogen bonding by itself. The water by itself is hydrogen bonding by itself. We put them together, now we find that, okay, now they're hydrogen bonding with each other, with both the solute and the solvent. And that comes back to our like dissolves like scenario. So meaning that, both solvent and solute participate in forces of attraction with one another, and the solute dissolves. For solute solvent solutions, involving matching of forces, the solute simply dissolves. This is known as a non-electrolytic solution. When we have solute solvent solutions involving ionics dissolved, or this new force of attraction, right, this ion dipole forces, this type of solution is known as an electrolytic solution. So we could really simplify this to say an electrolytic solution is one that contains ionic solute dissolved, and the solution can conduct electricity. Right, this is what we look at like Gatorade, Powerade, those types of things. If you read on the back of it, or even listening to their commercials, we got electrolytes, right? What are electrolytes? Electrolytes are just salts, right? Just because Gatorade, if you look at it, or even Powerade, right? If you look at the back, there's a lot of salt, not just sodium chloride, but other types like potassium phosphate, etc. And so all of these salts create an electrolytic solution, and Gatorade jumped on that idea with a buzz term such as electrolytes in terms of commercial play. We then have the non-electrolytic solution, and this would be, is one that contains covalent solute dissolved. And basically now the solution cannot conduct electricity. So, in terms of these different types of solutions, how does the electrolytic solution work? Well, it's because we have, ions in solution, plus and minus. And so that allows for electrons to travel through that solution because it's bouncing from the charges on one to another, going through the solution phase. We don't see that with non-electrolytic solutions because we don't have dissociation, right? We're not putting charge into solution. We're just simply dissolving a molecule. Here's an example, just a visual example of these two types of solutions. So here we have, a setup. If we look at the left pane, here we have sugar. In this case, a disaccharide, the C12H22O11, and that is what's in our solution at the bottom. And so here we have a circuit that's actually drawn with the red positive coming in to the battery. We see then that electrode goes up into solution, and so the other electrode is then connected to a negative, right? And so this is where we are now getting our current, but we have a break in the circuit with the two anodes. And that's the same for all of these. So they have a circuit, but if we were to look at the beaker with the liquid in it, we would have one circuit going off this way to our light bulb, and then we have another electrode here, and that's going off, right? So we have this separation between the two. So you put sugar in solution, nothing happens. If we put sodium chloride on the far right, notice that now we have an ionic molecule, and we can see that in terms of these different positive ions as well as negative ions that are in solution. And that's what now allows for the light to come on. Now here the circuit is connected. And that's because of those ionic molecules, sodium chloride, that are dissolved, these ions. So, due to ions in solution. So, as a result of that, we actually do have now a connection essentially occurring between the two electrodes that are in solution. If we look in the middle, we have something that is now what we would call weakly ionic. And this is a little bit getting ahead of the game here, but this is a weak acid. This is acetic acid, and unlike sodium chloride, which completely dissociates into solution, acetic acid does dissociate because it's an acid, and eventually we'll get to the type of terminology, but it's weak. So we don't have as many of the ions. We have some positive ones, we have some negative ones there, but they're few compared to what we see with the ionic system. With the ionic system, we had a lot more of those positive and negative charges because of this full dissociation that's occurring. So there still is a connection. It's just a little bit weaker because there's less of those ions in solution. And you can see that with the light, essentially having no light with the sugar on the left When we just have a few ions in solution, we get conductance, but the light is dim, and that would be the acetic acid in the middle. And then on the right, we have full ionic solubility, and so we see the light being very, very, very bright. So that is, example of these non-electrolytic and electrolytic solutions. And so we see that here with our non-electrolyte or non-electrolytic solution. And then we come all the way over to something being very strong. So that's the idea of this type of solubility. Things that are covalent just dissolve, right? And we see that with the sugar molecule being surrounded by the smaller H2O molecules. For ionic systems like sodium chloride, well, they dissociate into their relative ions, and now that allows for conductance, and that's an electrolytic solution. And then we'll get to acetic acid in a little bit, but just realize that there are some molecules out there that are covalent and do some dissociation, but we look at this as more of acid-base chemistry, and so we'll be talking about that shortly.